to this computer. Excellent. And yeah, so today's topic is about work. And so we saw in the pre-class videos that in order to find work, you want to integrate the force function. And so that's kind of the most general form. And of course, here's a little reason why. I mean, it's essentially force times distance, but if the force is changing depending on where you are, then again, you need to kind of add these up at each point. And if you do that and, you do this infinitesimally, then that's, the integral. And so that's why this works out. Haha. There are kind of 3 levels of problems, and I really break that down in our in-class notes today. Goodbye, swashbuckler. The first kind is either when the force is given, the force function is either given exactly to you, or I would put also like the Hooke's law style questions in this, because the Hooke's law, the force has a set formula, right? Force is equal to K times X. And so you don't really have to dig for it at all. So that's the first type of question. The second type of question are these kind of cable questions or rope questions, things like this, where you have to really dig to find your force function. It's a little bit of a guess and check. It's a little bit of, an ad hoc sort of method here. And then finally, the third type of question that we see are these liquid pumping problems, where you have some pump, right? And it's pumping liquid, and you want to know how much work in total it takes in order to get this out. This has an additional equation right here that you should have well memorized, especially as you move to do the web work homeworks and things like this. All right, I see a couple of folks with raised hands, so I'll go ahead and open it up for questions for just a minute or so, and then we have more problems to go over today. So yes, Jeff, you're up if you'd like to ask a question.
Yes, on example 5.4.6, the sigma is given in foot-pounds.
Yes.
But all the measurements are given in meters, and
oh, yes.
Any other conversion, you just went to feet.
Thank you. That's a typo. That's a good point there.
Okay.
So yes, these are all supposed to be feet. I assure you on quizzes and exams and things like this, we're a lot more careful. We're a lot more paranoid, I would say, about making sure that the phrasing's correct. So that way, yeah, you don't have to sit there and waste time thinking about what's the conversion from meters to feet.
Right.
When they're the in-class problems or the pre-class problems, sometimes I have a tendency of being less careful just because I know that I can always say words in class to, expand on these sorts of things. So yeah, thank you for pointing that out though. Okay, excellent. And let's see, Catherine, you're up if you have a question still. Your hand was raised. And then we'll get into the new stuff. You are muted, by the way. Oh, no question. Okay. No problem. Okay. Any other interesting questions in chat that we should talk about quickly, Yuan?
In Q&A, someone is asking about the practice problems we could do before the exam and the quiz for review. I think yeah. Mm-hmm.
Yeah, I think that, we're quite intentional about having the assessments build on one another. And so I think that many of the problems in web work, sometimes the learning set problems, especially as you read the syllabus, the learning set problems does contain some easier problems and some more difficult problems, right? And that's good for a learning set. But for the time set stuff, that kind of hits the Goldilocks zone, maybe a little bit soft, maybe it's a little bit on the easier side. We also give you a little bit more time, but I would say the web work homework's good. That's one of the great uses of the textbook. So buying the textbook and having that, again, this is the full textbook, and this has Calc 1, Calc 2, Calc 3, all the text that we use in one. It's a big, thick textbook. And we use the old edition, the 7th edition, so it's only $20 on Amazon, last I checked. So yeah. Yeah, the quiz is on 5.2 and 5.4. So yeah, doing the web work homework ahead of time and taking a look at those questions are great. I have a question. If I can speak up a little bit, I'll try to move the microphone closer. But yeah. Okay.
And there's someone asking about if they missed the live lecture, how much of the video do we have to watch for credit?
You should watch all of it, but we try to be somewhat generous on this. So we're looking for probably at least 15 or 20 minutes. So even if someone's doing it at double speed or something like this, you would still get counted for that. But yeah, make sure you don't want to just click on it and like leave or something like this. You want to actually put some time into that in order to get the credit for watching it on D2L. Okay, well, with that, we have some new problems to cover today. Where are they? Here they are. So again, I've kind of been very explicit on this when it comes to the problems, at least in class. So level 1 problems, at least what I'm calling them, are stuff where you have the springs or spring-like objects, so rubber bands, stuff like this. So stretch 3 centimeters beyond its natural length, the spring exerts a restoring force of a magnitude of 6 newtons. Assuming Hooke's law applies, how far will a force of 10 newtons stretch the spring? So an important thing here is that this, and some of the problems are like this, where it's not asking yet about work, right? So, I mean, the big thing here is about work. And in fact, part B, we get into work. But this right here is just asking another question about force. So again, it says Hooke's law applies. So force is equal to K times X. And you have a couple of pieces of information. So the main example text here says that stretch 3 centimeters beyond its natural length. We know what force comes out. So we have a force of 6 newtons if you stretch 3 centimeters. So this will give us that our K value is going to be 2. And again, you do kind of want to think about, especially if there's changing units or anything like this, what the units would be for the K value, right? Because again, force, this is newtons, and this is 3 centimeters. So if you want to be very explicit about this, this would be in newtons per centimeter. Luckily, though, as we go on to solving part A, right, we could just answer in centimeters. So, right, so the question is, how far will a force of 10 newtons stretch the spring? So if we do a force of 10 newtons, how far does it stretch? Well, that's a question of what is X, right? X is supposed to be that distance beyond, its natural length. How far are you actually stretching it? Notice that it didn't actually say how long what the natural length is for this spring, but we do know that this is supposed to be 10. And again, maybe I'll be very explicit here in this first problem, 10 newtons. Here, this is 2 newtons per centimeter. And here we have X. If we go ahead and divide onto the other side, so 10 newtons divided by 2 newtons per centimeter, and you can kind of go ahead and flip those units, right? And you're going to get 5 centimeters is going to be our value for X. So this is a relatively nice one. And let's go ahead and solve B, and then we'll open it up and see if there are any questions. So now that we know how far the spring is going to stretch, the question becomes, how much work does it take to actually stretch it this far? So this is where we actually need to use our work equation. Remember, work is the integral of force. In this case, it seems like we're using X as our variable here. So I'm going to say f of X, thinking of it as kind of some horizontal stretching of the spring. And we know that we're starting at 3 centimeters beyond its natural length, and we go to 5 centimeters beyond its natural length. So this is what we did with part A here. We also know, as we solved, right, what our force function is. So we know that force is going to be Kx. And remember, we found that the K value was 2. So this is just going to be the integral of 2x. So that has a nice integral, of course. That's going to be x squared. We evaluate from 3 to 5. And so we get, let's see, 25 minus 9. And so we get, what, 16. And here's where we have to be a little bit careful thinking about what our units are for this. Right, so all of our x's, and so importantly our dx right here, would have units of centimeters, right? Because again, kind of all of these had units of centimeters. And then our force function here, this had units of newtons. So the end answer here would have units of newtons times centimeters. And maybe that's a little bit strange. And in many web work problems, and even possibly in D2L for quizzes and exams, maybe it, gives a set answer with units of Newton meters, right? And so, of course, if we want to transform this into Newton meters, we can certainly do this, right? So this is Newton centimeters. And if we do 1 meter is equal to 100 centimeters, then we could go ahead and cancel out a little bit, and we get 0.16 Newton meters. Traditionally, though, we haven't really been so interested in change of units when it comes to quizzes and exams. Again, we're focused on, calculus. And so we don't usually spend a lot of time, at least on the timed assessments, quizzes and exams, or even the web work timed assessments with unit transformations. So I wouldn't worry about that too much. You may see 1, maybe 2 problems like that in the learning sets, because it is something in general that you have to be concerned with. But again, not so much when it actually comes to the big assessments.
Yeah, there's a question I think I want to ask, which is why are you supposed to start with 3? Why don't you start with 0 to 5?
Yeah, so that's a little bit in the interpretation of the problem. That's a great question, though. So I took this problem to mean that, it was already stretched to 3 centimeters beyond its natural length. So that's our starting point. And then we're going to stretch it to 5 centimeters. So kind of that's the problem text gives us kind of our initial setup. And then we go on to solve later on. We want to take it to 5 centimeters beyond its natural length.
Mm-hmm.
Let me see.
At the 25 minus 6, where does that come from? Something like, yeah.
Yeah, the 25 minus 9 is just inputting the those endpoints, the 5 and the 3, into our antiderivative. I also see here, let me clear a few top ones here. What does the star represent on X? So I'm assuming this is kind of a question that I missed earlier on here, but it has 3 upvotes, so we'll go ahead and take care of that one. Technically, when you define Riemann sums, there's a lot of freedom in your test points, kind of at what points that you choose in each subinterval. So this star right here means that it doesn't have to be a left-hand endpoint or a right-hand endpoint. Really, it can be any, and there's some technicality as far as the size of partitions and things like this, very technical things. But essentially what you need to take away really from this is that it's the normal Riemann integral that you know and love from Calculus 1. And then I'll also answer, do we need to memorize trig identities? There's just a couple of trig identities that you need to have memorized for like the quiz. For the exam, you get a formula sheet that has more trig identities, and kind of as we continue in this class, we'll do more stuff with trig. But the 2 big things that you need to have memorized for quizzes and whatnot is sine squared plus cosine squared equals 1. So not a super challenging one. And then you also need to know that if you divide through this by cosine squared, you get, well, sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared would be secant squared. Those are the 2 big formulas that you would need to know as far as memorizing trig identities. All right. So with that, let's go ahead and continue. I would like to pause for a minute and maybe give you guys a chance to get your hands dirty with this question here. So this is a multiple choice, which is certainly something that, we can plug into D2L and things like this. So I'm going to give you 90 seconds or so to attempt this question on your own, and then we'll come back together and solve this one as a class. Meantime, I'll try to type up some answers for the Q&A and help out you, Yuan.
I'm sorry?
I was just going to say.
You're also typing the questions, answers?
Yeah,
Okay,
I'll help
that'd be
doing it
great.
too.
Yeah.
All right, that's probably been enough time here. Let me show you the wrong way to do this. And then, you know, I'll show you the correct way. Hello, cat. So it took 24 joules of work. Remember that joules is another way to say Newton meters. So you could say this is 24 Newton meters to stretch a spring from its natural length of 1 meter to a length of 2 meters. So let me go ahead and set this up. And again, maybe I should do this in red or whatnot. I said I was going to do this incorrectly first. So Newton meters. And remember, so this is work, and we know the formula that work is supposed to be equal to the integral of force. So this is the equation that I'm setting up here. Work is the integral of force. So it took 24 joules of work. So that's a unit for work. So, okay, we need to integrate force. This is a spring sort of problem. So Hooke's law is going to apply. So K times X dx. And the question is, what is that spring constant K? So this is what I'm trying to solve for. It says that we're stretching it from 1 meter to 2 meters. So 1 to 2. And let's see here. So if I integrate this, I get K over 2x squared from 1 to 2. K over 2. Let's see, if I plug in 2, 2 squared is going to be 4. If I plug in 1, 1 squared is going to be 1. K divided by 2 times 3 equals 24. Hello, cat. Thank you. So let's go ahead and divide a little bit. So we get 8. And so here I get my final answer of 16 once I multiply by 2. Meters there. Newtons was in my embedded in my joules, right? Those are Newton meters there. So yeah, K equals 16 newtons per meter. Seems like my correct answer of C. And this is the wrong way. Well, this is an incorrect answer. And so my question for you all is, can anyone spot my mistake? Four minus 1 is fine. Yeah, so a few people are getting it here. I say that this includes some extra information, right? It says that we're stretching the spring from its natural length. Remember, X is not just any old distance. It's distance away from the spring's natural length. So when you say its natural length is 1 meter, that means that we're starting off at its natural length of 0 meters from its natural length. So yes, and then of course 2 meters, that's going to be 1 meter beyond its natural length. So the correct setup, and I'm not going to write my units here, is actually integrating from 0 to 1. And when you do this, let's see, plugging in 1, plugging in 0, you just get 1. And so you get K is equal to 48 Newton meters. So the actual answer is E in this case. So yeah, as several students pointed out, yes, reading the questions carefully, slowly is sometimes critically important with stuff like this. Remember, X is, again, not the actual length of the spring, but it's the distance beyond the spring's natural length. And so, yeah, I see a question as far as up here, why didn't we use 0 to 2 or something like this in this previous one, right? 3 was not its natural length. It was 3 centimeters beyond its natural length. In example 6 here, we didn't actually specify what the spring's natural length was. So you do have to be prepared for kind of either one of those sorts of deals there. Yuan, any questions in chat, or not chat, Q&A that we should talk about?
Someone's asking, can we use the equation, the W equals K over 2x squared directly?
For Hooke's law sorts of questions, absolutely. But we're about to go into level 2 sorts of problems where Hooke's law doesn't apply anymore. And so, yes, for these sorts of ones, if you just want to memorize something else, you certainly can memorize something else. I don't think it's so necessary. I think really coming back to just Hooke's law, force equals K times X. And then, you know, anytime you want work, you need to integrate that. So yes, you can. I don't think it's super necessary.
So someone is questioning the force, the relation between the force and the K, and in particular, what's the meaning for the K? Yeah.
So yeah, the meaning for the K, it really, you can see it in its units here, right? The units are newtons per meter. So that is how many newtons of force would it take to stretch it, you know, to the next meter. So newtons per meter. So yeah, that's the meaning of K. So if you have higher K values, you essentially have stiffer springs that require a lot more force and resultantly, you know, work in order to stretch them farther and farther. If you have a smaller K value, then you have kind of a weak spring. That's the meaning for K. Okay, and I see one hand raised. Why don't we go ahead and take a verbal question, and then we'll move on to the level 2 stuff. Catherine, you're up if you have a question. All right, maybe it was a error again. That's fine. Okay, so with that, why don't we go ahead and move on to the level 2 types of questions, work for cables, ropes, etc., things like this. Again, these ones you don't have kind of a general formula to use. You really have to derive and kind of think about your situation in order to come up with your force equation. So your worker is about to pull up 30 meters of hanging cable. So I always imagine that there's, right, the cable's like hanging off of a ledge or something like this. And you have 30 meters of it, right? And you're about to pull this cable up. How much work will it take if the cable weighs 2 newtons per meter? And so I want to think a little bit about the force function. And you can use y as your variable because we're like lifting it upwards, you know, to on top. And again, kind of you think of that the cable is going to be kind of coiling behind you. So you don't have to like continue holding on to that and continue and applying force or work to that cable that's already been lifted up. But let's think a little bit, my y is going to be how much I've already lifted. So if I think about how much force is being applied if I haven't lifted any cable, right? 0 is how much I've lifted up so far. Well, it's 2 newtons per meter, and we have 30 meters. And so all 30, right? I haven't lifted up any yet. So all 30 meters is still hanging off of this cliff, and it's 2 newtons per meter, right? So 30 meters times 2 newtons per meter, right? The total force is going to be 60 newtons. Let's think about if I've lifted up 1 meter. So I've started to do some work, right? And I've lifted up 1 meter. And right, so there's 1 meter coiled behind me, sort of deal. And still there's 29 hanging off, right? That's applying force, right? I have to counter that force of gravity with my hands. So still there's 29 meters hanging off. And each one of those meters weighs, well, 2 newtons per meter. And so this is going to be 58 newtons. And you can kind of play this game for a while, and you could even ask, well, when are you kind of done? When have you lifted all of the rope up? Well, that's going to be at 30, right? Once you've lifted up all 30 meters of cable, hopefully, right, it's all coiled behind you or whatnot, there's 0 newtons left. And so we need to figure out a pattern, right? An overall pattern for our force function. And so my question to you guys is, what is the pattern for this force function? And my hint to you is that it's going to be linear. And in fact, I see a lot of folks who are coming up with it. That yes, if you haven't lifted up any already, you have 60. And for each meter that you lift up, so if we're using a variable of y for how much we've lifted up, right, it's minus 2 newtons per meter times however many meters that you have already lifted up. So this right here, again, I said that for these sorts of problems, I call them level 2 problems because you have to think about them for a little bit. You have to almost kind of guess and check to come up with the correct force function. Once you have the correct force function, though, the work that you do, I guess pun intended there, in order to get the work value is the exact same, right? You integrate the force. So you integrate force. In this case, we want to lift up all 30 meters of rope. We started off by, all 30 meters was hanging down, and we want to lift it all up. So we want to lift from 0 to 30 the meters, all of them. And so we can integrate this, find the antiderivative. Oops. 60y minus y squared. Evaluate from 0 to 30. Of course, when you plug in 0, it's not very exciting. You just get 0. When you plug in 30, let's see, we have 60 times 30 minus 30 squared. Well, I know 3 squared is 9, and 10 squared is 100. And so let's go ahead. 30 times 60, well, 3 times 6 is 18. And we got a couple of zeros. So let's see, 900, and this was, again, newtons and meters. So Newton meters. So my final answer here is 900 Newton meters. So again, once you know what the equation is to actually integrate, it's very similar to our previous questions. The added difficulty here is really figuring out what to integrate. And so sometimes you have to play a little bit of a guess and a check sort of deal. A hint for these ones is that they all turn out to be linear. So that's quite nice in this case. I see a few raised hands. Why don't we go ahead and take a few questions? Jackson, you're up if you want to vocalize your question.
So can the equation just be 2y if I end up getting the same answer?
Yes. So there are other ways to set this up, although maybe your units end up being a little bit strange or kind of high, because I literally think of it as, first of all, I haven't pulled up any rope, right? Or any cable in this case, right? And kind of as time progresses, I've pulled up more and more cable. You can do this where you've just integrate 2y, but then your variable's a little bit changed, right? It's kind of how much rope you have left over, or yeah, how much rope that you have left over. So you go from 0 to 30, and yeah, so it works. It does work. It's just, it's not as intuitive. And actually, we're going to make some connections, I would say, with, well, sorry, it's not as intuitive for me. For other people, it may be actually more intuitive, and you're certainly allowed to use that method. But we're going to be able to make some connections with what we're doing here to these liquid pumping problems. And so that's maybe a more convincing reason of why I want to demo it in this way, is because we're going to be able to make a connection for a harder problem later on.
Okay, thank you.
Yep, no problem. All right, I'll take maybe 2 more questions here, and then we need to move on. So Teresa, you're up if you'd like to vocalize your question. Hello? Sorry, Teresa, I can't hear you. So we're going to go ahead and skip and go on to Juan Campbell. You're up if you have a question.
All right, can you hear me?
Yes.
All right. So I just want some clarification. So one, how do we end up getting f of y to be 60 minus 2y? And when it comes to getting like your bounds, how do you know like is it gonna be 30 and 0? Are you just straight up choose it from like the problem and
Yes.
then like assuming it's from 0 from there?
Yeah, so it goes back to something that I didn't exactly write down, but is important, right? That y meant, right, that variable is how much rope or cable I've lifted. And kind of all of your questions really come from that. So I said these words, but I didn't write it down anywhere. So I want to lift all 30 meters of cable, right? Initially, it's all hanging off of this cliff or wherever, or elevator shaft or what have you, right? And so I want to pull up all 30 meters of the cable. right? And so that's why my bounds are from 0 to 30, right? Initially, I haven't lifted up any of it, and I get to go home once I've lifted 30 meters, right? So that's where that comes from. Your second question is, how are you able to determine that? Well, really, it was your first question, but it's a more complicated one, so I kicked it down the road a little bit. How are you able to determine this formula? And this was, right, it's complicated, right? It's a little bit of a guess and check. And that's kind of the difficulty in these sorts of problems, is that you have to think about the actual real world situation and think about kind of as things change, right? So as I haven't lifted up any rope, right? How much force is there? If I've lifted up a little bit of rope, how much force is there? What is a general equation that relates together how much rope I've lifted or how much cable I've lifted versus how much force is being applied by the remaining cable? And so because it weighs 2 newtons per meter, this is kind of the critical thing, that this is linear, right? And so for each meter that's hanging off there, whether it's 30 still, whether it's 29, so on and so forth, right? There's 2 newtons per each one of those meters hanging off. So initially there's 60 newtons of force. And then for each meter that I lift up, 2 newtons go away, right? Because that cable is no longer hanging off of my cliff. It's coiled up in a pile behind me. I don't really care about it. I don't have to apply force to that cable.
Oh, okay. Thank you. I appreciate it.
Of course. All right. Well, with that, why don't we go ahead and move on to another problem here. This one, again, kind of, it's similar to a problem on web work, and it's a cable or rope problem. I'd like to give you guys maybe 60 or 90 seconds. Maybe you guys have already started this a little bit, but please work on this problem for a minute, and I'll try to help out in the Q&A for just a minute, and then we'll go over this one together. See, I'm betting that's your pencil or something, but it almost sounds like you're whistling, Yuan.
Oh, I'm sorry.
No, it's all right.
Is there a car for the elevator problem?
So this one, it doesn't have any weight given to the car.
Mhm.
So in particular, it's just asking lifting the cable.
Mhm.
So yeah, there would, in a real situation, you would of course have weight given to the elevator car as well, but we're just interested in the cable. All right, let's go over this one together, guys. It's very similar setup to the last one. just different numbers and, slightly different words here that we have, this elevator car and all that sort of stuff. In order to come up with work, we want to integrate force. The cable is 100 feet long. We're starting off at the first floor, and we would like to get it so that, we've lifted all of it, right? So we've gone from the cable being, 100 feet long to 0 feet long when it's at the very top floor. And so again, Y is going to be how much cable we've lifted. And luckily, I'm not the one doing the lifting this time. It's an actual motor or something like this, but still, maybe you want to convert this into how big of a motor you need or what have you, how much it's going to cost to run your elevator, anything like that. So again, kind of you need to come up with what is your force function. So you can set up something like this. It's 100 feet long, right? So when you haven't lifted up any of the cable, you have all 100 feet dangling down the elevator shaft. And it's 60 pounds per foot. So 60 pounds per foot, that's the 60 there, 100 feet long. So this is 6,000 pounds. That's the unit there. That's the weight, the force that's being applied. And of course, when you've lifted it up by 1 foot, then you only have 99 feet hanging in the elevator shaft, right? And the other cable or whatever is coiled, hopefully on a roll or something like this. And so you're going to have 5,940 pounds. So on and so forth, all the way down to once you've lifted up all 100 feet of cable, of course, there's going to be 0 pounds of force left over, right? There's going to be no cable dangling. And so if you do a similar setup for last time, right, this is going to be 6,000 minus 60 times Y, times how much you've lifted up. That's going to be your general force equation. And I'd like to show you guys, because like I had mentioned earlier, someone else had brought up, why am I choosing this way, right? There is a way that you can do this where maybe this formula isn't quite as complicated. But this will go into kind of our future problems down here, where you can think of this as density. So the density is 60 times the distance. So if you factor out that 60, the distance would be 100 minus Y. So again, you can think of this as density. 60 pounds per foot. And this right here is the distance, right? So for instance, if you haven't lifted up any, right, there's some at the very bottom that has to be lifted up 100 feet. And there's some, 1 foot up that has to be lifted up 99 feet. So density times distance. And I guess the big thing here is that that's linear density, and that will become important later on. This should, of course, look very, very similar, right, to this, right? If I go back to our chapter 5 filled in notes, you guys already know this formula for the pumping problems. This was density. And this is not linear density, right? This was something like newtons per cubic meter. And this right here is distance. So because the rope is kind of, right, we don't really have any width or length to the rope. It just has height sort of deal that you can kind of think of. The dimensions are a little bit different, so you don't need the area here. If we had the rope instead of, newtons per meter or pounds per foot sort of deal, then you would need to know the cross-sectional area of the rope in order to get the full equation there. So these things are certainly related to one another. So you don't have to think of them as all like disjoint problems. There is certainly relationships with all of this. Either way, this is the setup. When we go ahead and integrate here, we get 6,000y minus 30y squared. Plug in 0, plug in 100. So let's see, 6,000 and what we sprinkle on 2 more zeros when we plug in 100. And 30 and let's see, 100 squared. So that's going to be 4 zeros in total. So this is going to be, let's see, 600,000 here minus 300,000. So the final answer is 300,000 foot-pounds. where did the 30 come from? The 30 came from when I took the antiderivative of negative 60y. So remember, you need to divide by 2 there in order to get that. Any questions in chat that are coming up about this, or should we move right on into the level 3 stuff? Or I guess not chat, Q&A.
It looks good here.
Okay, well, we have a few people raising their hands. Let's go ahead and call on a few people who haven't been called on yet.
But Ethan said he probably got the same answer in a different way. Yeah.
Yeah, there's definitely different ways that you can go about solving this. Arian, you're up if you'd like.
Hi, can you hear me?
Yes.
All right, perfect. Couldn't you just use 60y and just integrate that? Then you get y squared divided by half and multiply by 6, you get 30y squared. And if you just square 100 and multiply by 30, you get 300,000. And that's like 3 steps at best. Yeah,
I mean, this is very similar to what the other person brought up for example number 8. That yes, if you set your variables differently, instead of how much cable I've lifted, maybe how much cable is remaining, then the force function is different. And yes, that also will work out. But by choosing to do it this way, we can see that there's a connection actually with this liquid pumping problems, which are more complicated problems. And that's what I wanted to kind of reinforce here.
So it's more intuitive to do it that way for future progress.
Yes. I quite often like to choose the method that can be expanded the most, that can be used in the most number of situations. So sometimes there's like shortcuts for very particular types of problems. But I don't know, I don't like explaining lots of different methods, right? I like to choose one method that works in many situations.
All right, great, thank you.
Mm-hmm. All right, and one more question here, and then we'll move on. Aditya.
Hi. Just a quick question. So I don't know if it's just my physics brain doing this, but when you say that the cable weighs 6,000 pounds,
yes,
like, and you also say that that is the force, I'm like, that's kind of like, I don't know, just me going like physics is like force is equal to like mass times acceleration. So when you do weight, you do multiply 6,000 by 10 or 9.8, right? So like, why is this why do we just take the weight here as the force?
Yeah, and in fact, if you read the textbook, for this section, there are problems that they go into where they bring in the gravitational constant, whether it's 10 or 9.8 or 9.81 or stuff like this. And then of course, 32 for the feats and the, all that sort of stuff. And so you can really get into playing with units quite a lot if one is so inclined. And luckily, I would say for the most part, we've been able to eliminate all those sorts of problems from our web work, quizzes, and exams. We used to have them in here. And so, yeah, we're just kind of, we really want to focus on the calculus. And so, yes, you can use, pounds as the weight or the force. And here it's a measure of force. Does that kind of make sense? At least from what we want.
I think so. We just like, because the way we do physics problems, like when we did work in my physics classes, when we found the force, we'd use multiplied by like 9.8. And then to get the work, then we'll multiply it just what we did. But we multiply like, sorry, I'm stumbling on my words here. So basically in my physics classes to find work, we'd multiply weight by like 9.8 and then continue what we did with the integral. So like we would,
yeah, we have to be careful because weight versus mass, right?
Yeah.
And so we're really using this as weight, not mass.
Okay, so 6,000 is the weight, not the mass.
Exactly. Yes.
Okay, got you.
Cool. All right. So let's move on. We definitely owe it to ourselves to at least do one, ideally more than this, of these level 3 problems, right? So if we are pumping liquid, these are the most complicated style of problems. And so they'll take a little bit of time. And remember that there's an additional formula that I would recommend that you have memorized here. And that is for a particular type of force. So this again is some force function. It still is related with what we've been doing throughout this entire class. And this force function is dealing with pumping liquid. And so first of all, you need to know maybe like the density of the liquid. So again, this sigma right here is density. Sometimes I've seen sigma, a lowercase sigma being used. In other cases, I've seen a lowercase delta being used. For whatever reason, it's always a Greek letter, it seems. But okay, our book uses the sigma, so we'll stay consistent with that. You need to know the cross-sectional area. So this is cross-sectional area. And this may change. So in particular, for our situation here, for different y values, let's go ahead over here and say that this is going to be at y equals 0, and this is going to be at y equals 10. So you do have to kind of specify where everything lives. So if this is y equals 0 and this is y equals 10, of course, if you have small y values that are closer to 0, your cross-sectional area, right, as you take a cross-section for a particular y value, so let's maybe say that this is at y equals 1, and later up here we could do y equals 5, we can see that that area is changing. They're all circles, mind you, so they do have a nice area formula, and we're going to be leaning on that hard. But that cross-sectional area is changing. It depends on what y is. And so that's why we're using that function notation, a of y. Area, but it depends on what y is. And then finally, times the distance that you actually need to pump that cross-sectional area. And so this is distance to pump the liquid. And then, of course, we're going to be integrating this with respect to y. So distance to pump. So for instance, if we were thinking about the stuff at the very bottom, right, that has a height or a y value of 0, according to this problem, we want to pump it to the top, and then we want to pump it 6 feet beyond the top. Apparently, that's where the spout for our pump actually exits or whatever. And so this is going to be 16, right? The distance that you actually need to pump here is going to be 16 versus if you have the stuff at height 5, the distance that you need to pump for the layer at height 5, well, you take that full 16, but it's already sitting 5 feet up. So it would actually be 11. You need to pump that 11 more feet up. And likewise, the stuff at the very top here, this only needs to be pumped 6 feet. And so it really depends on kind of where that cross section lives, right? That you only need to bring it up, so much higher. Okay, so with that, let's go over how I would set these things up. And I always like to work, from the easiest things to the hardest things. And that's just kind of a habit of trying to maximize partial credit. And so in this case, I think that the easiest thing on all of these sorts of problems is the density, right? The density always is just a number that's given to you. If it's oil, then you can get maybe a more creative number. If it's water, well, you should look that up and you should use the right number. So it's 62.5 pounds per cubic foot is the density there. 62.5. The cross-sectional area is the most difficult bit. That's the part that I'm going to leave for last. The distance is always a linear function. It's kind of very much, like these cable problems. And so as we saw here, the stuff that's at height 0, it needs to be pumped a distance of 16 feet. The stuff that's at height 5, it needs to be pumped 11 feet. The stuff that's at height 10, it needs to be pumped 6 feet. And so it always seems to be 16 minus the height that cross section lives at, right? So whatever that 16 is, that's the total, the 10 feet plus the 6 feet, because we're going 6 feet above the top. So that's the 16 minus however high it already is. And you can, of course, double check, be paranoid when you're coming up with these things, guess and check. And so check, if you plug in 0, you get out 16, good. If you plug in 5, you get out 11, good. If you plug in 10, you get out 6, good. dy. Now we need to think about where we actually need to do the pumping, right? And this is a common mistake that I sometimes see. I see folks say that you need to do the pumping from 0 to 16, right? After all, right, you need to take it all the way up to a height of 16, and you're starting off at a height of 0. However, there's not any liquid up here, right? Y is where, the liquid actually exists. You're taking into account that you need to pump it up 6 meters beyond the top of the tank by using this distance right here, the 16 minus Y. You don't need to take it into consideration twice. So really the liquid only exists between 0 and 10. That's really where you're doing the pumping, right? That's where you really need to apply the work. If you do from 0 to 16, it implies that there's actually more liquid up here, which there's not. All right, so we've done all of the easy stuff-ish. Now we're on to this tough stuff, really, and that is how do we relate together, right, this cross-sectional area here? Well, we can see at each one of these heights that it is going to be a circle. So I know that the area is going to be given by the formula pi r squared. But the problem is, right, and I could plug this in, but we run into this situation much like we had in 5.2 when we were doing stuff about volumes, right, where we're only really allowed for one variable. And so our one variable here is y. That's the thing that we're integrating with respect to. We need to get r squared in terms of y. I need to make some kind of trade here. And so it really helps to have a picture. We already have one, great. Let me go ahead and draw in a few more things. So let's say this right here for some, arbitrary height, this is the y value. We have the radius of the circle. You have to be a little bit careful because there's a radius of the circle, the cross-sectional area bit, and there's also like the overall radius, right? We know that the overall radius for this sphere is going to be 10. It's a sphere, and again, it's a sphere of radius 10. So if you take any distance from the center of the sphere to a point on the sphere, again, kind of that needs to be constant. That's the whole thing with the radius. And so we know that's going to be 10. So we need to relate together this y and this r, how high up you are versus what is our kind of two-dimensional radius, the radius of the circle, not the radius of the sphere. And so we get this sort of picture here. And what I find is that I would like to kind of, instead of use that y there, I see that this is actually part of a right triangle, right? If I go ahead and include this right here, we can see that there's a right triangle lingering here. We know that this overall length here, this is going to be one of our radiuses of our sphere. So the overall length here is 10. In fact, I don't even need to write that. It's written right here. And so if you go up y, the bit that's remaining is 10 minus however far you've gone up. Notice if you take these and add them together, right, you get 10 overall. And so let me go ahead. I want to clean this picture up a little bit. I want to just move it over here. We have 10 minus y, and we have r, all in a nice right triangle. And so I've just copied this picture, but I've only taken the important bits for me. And because it's in a right triangle, we know that one equation that we could relate these things together with is the Pythagorean theorem. So that is r squared plus the other leg's length squared is equal to the hypotenuse squared. And again, we wanted to get our area formula in terms of y. We wanted to get rid of the r squared, but we had this wall of what should the right trade be between these things, and here it is. So why don't I go ahead and rearrange. And now we can go ahead and trade in for r squared here. And so this is going to be pi, and r squared is the same thing as 100 minus 10 minus y quantity squared. Kind of writing off of the edge there. But I'll go ahead and clean that up once we put it in our full answer here. 0 to 10, 62.5. And the area formula for my circle there that uses y is pi times the radius squared. And again, the radius squared was given by 100 minus 10 minus y quantity squared. Plug in the distance, integrate that with respect to y, and you win the game. Now, this problem here asks to set up, right? Just set up. You do not need to evaluate out the definite integral. So certainly in D2L or web work would be a lot easier, but in D2L, right, this could be done with a multiple choice, or there could be just a few missing pieces where you have to fill in the blanks for that. Or it could just ask maybe specifically about the cross-sectional area or stuff like this. So there's a couple of different options. If we really wanted to ask this question in D2L, right, the easiest way would just be a multiple choice. And this is one of the answers there. All right. So yes, I see that I'm over time already. This is where well, I'll keep the recording going for a little bit, and then we'll turn off the recording and take any more questions that you have. But let's see, I have one person raising their hand. I'll go ahead and call on you. Andrew, you're up if you'd like to ask your question.
Hi, I thought, isn't it pi r squared? So you should square the outside of the whole parentheses, and 100 minus 10 minus y squared.
If we had solved for r, absolutely. But notice that what we solved for here was actually r squared.
Oh, okay.
So then you don't need to re-square it or anything like that.
Right. Okay. Makes sense. Thanks.
Cool. Yep. Let's see here. Teresa, you're up if you have a question you'd like to ask. I still can't hear you. I hear noises. Maybe this is you on though.
I'm typing.
Yeah. I'm sorry, Teresa.
Sorry.
Yeah, sorry, Teresa. Something's up with your microphone. You may need to unplug it and plug it back in or something like this. But this happened the last time I called on you too. So we'll move on. If you want to fiddle with your computer a little bit and raise your hand in just a second, I'd be happy to call on you again. Sam, you're up.
Oh, hello. Can you hear me?
Yes.
Oh, all right. I was just going to ask, there's this problem on the woodwork.
Yes.
That it gives you the density in, I think it is, I can't remember exactly, but I think it is newtons meter squares.
Yep.
And then it asks you for an answer in joules, as far as I remember.
Well, remember, joules is the same thing as Newton meters.
Is it? Okay.
Yes. So we use that back up here. 24 joules is the same thing as 24 Newton meters.
Oh, okay. So in the case that they give us the density in this case, newtons, in this case, meters squared, or I think it is cubed actually.
Yes.
Should we just approach the same in the same way?
Yeah, definitely.
Okay, thanks.
I mean, all of it would be in meters and all of it would be in feet, but remember, then in feet. But remember, in our class, we don't really want to spend a lot of time worrying about unit transformations. We're really about the calculus.
Sure, sounds good. Thanks.
Michael, you're up.
Can you hear me, Mr. McCombs?
Yes, I sure can.
Okay, just double checking. So the quiz next Tuesday is going to cover 5.2 and 5.4. Am I right in saying that?
Yes, absolutely.
Okay, thank you. That's all I wanted to hear.
All right. Yeah, no problem.
Have a nice weekend.
Thanks. You too. This is probably a good place. I'm going to stop the recording, but we'll stick around and still take a few more questions here. So.